Hey guys, my name is Tensor. Welcome back to the Golang blockchain tutorial series. This video will be part 7. Today we're going to do a little bit of optimization for the persistence layer of our application. Essentially, we want to create something called the unspent transaction output set. As our application scales out and as we have more and more blocks getting added to our Badger DB, this process of trying to check every single transaction becomes more and more inefficient. If you look at Bitcoin, for instance, the amount of space that all of the blocks inside of Bitcoin will take up on a disk is approximately 200 gigabytes. This means to just validate a transaction, you need at least 200 gigabytes worth of space for Bitcoin. At least that's what it would mean if their system worked like ours did. The solution to this problem, however, is to only really index the unspent outputs and then search through those unspent outputs for very specific things. Here I've got this 3-block diagram. And you can see we've got our Genesis block, then we've got block A, which has one single unspent output, and then we've got block B, which has 2 unspent outputs inside of it. When the Genesis block is created, there is a single unspent output. The person who mines that output has access to that unspent output, and their balance is based on how many tokens are inside of that output. When they go to send tokens to another user, our application needs to find that unspent output and then use it to create the next transaction's input and then the next outputs attached to that transaction. So say user A sends 50 tokens to user B, then we would have 2 outputs, one with 50 tokens inside of it, belonging to user B, and another one with 50 tokens in it belonging to user A in the next block. And so as you can see, these unspent outputs are pretty special. They're pretty important because we can use them alone to decide how many tokens a user owns and which tokens that user can move around. To get started with our code, let's go into our tx.go file and create a new structure called txOutputs with an S. This will contain an array of transaction outputs, and we can use this to identify our transaction outputs and then sort them by unspent outputs. With this new structure, we can create a serialize and deserialize function so that we can take the actual structure and decode it into bytes and then re-encode it back into the Go structure. These two methods look exactly like the other serialize and deserialize methods that we have inside of our application. In the case of serialize, we create a bytes buffer, and then we use the gob encoder to encode the bytes, and then we just pass back the bytes. In the case of the deserialize function, we get a bytes reader to read in the data, and then we create a gob new decoder, and then we decode the bytes back into our Go structure type. With these helper functions and this helper struct created, we can now go and create the main structure for our unspent transaction output set, which we'll just call UTXO set. So the UTXO set contains a blockchain field, and that's it. This allows us to access the database that's connected to our blockchain, and then we can create a new layer inside of that database which will have just the UTXOs. When we were building the database for our blockchain, I mentioned that Badger does not have any tables. The way that you can sort of separate data inside of the Badger database is by creating prefixes for the keys that you put into the database. So up here I'm creating a UTXO prefix, which will be a string of UTXO dash converted into a slice of bytes, which we can append to the front of each of our prefixes as we put them into the database. This way we know which pieces of data in our database are attached to this UTXO set and which ones are attached to the blockchain itself. And the main reason why we need to make this differentiation is because all of our data is going to be held inside of the same files. Also, while we're at it, just to make this a little bit easier, let's just create a variable for the prefix length. So we just take the UTXO prefix and call a length function on it to get that number. To get started here, I just want to create a delete by prefix method, which will allow us to go through the database and delete in bulk the prefix keys from the database. And because of the way that Badger works, we need to do this in a very specific way. First thing I'm doing inside of this function is creating a closure and binding it to the variable of delete keys. This closure takes in a two-dimensional slice of bytes, and then it outputs an error if there is one. We can access our blockchain's database by calling to U, which is the UTXO set struct, then calling blockchain database, and then we can enable a read-write transaction by calling the update function and passing in a closure which exposes the Badger transaction and then passes back an error if there is one. Inside of this read-write function, we want to iterate through the two-dimensional slice of bytes, call transaction delete on each of the keys that we get back from our two-dimensional slice of bytes. This may look a little bit more complicated than it is because we have all of these if statements, but all this is really doing is it's running this part of the statement, so it's always going to run the update function. However, if we have an error and that error is not equal to nil, then it will just return the error. Otherwise, it will return nil. And this is also the case for the if statement inside of here. So this is always going to run the transaction delete on the key, but if we do have an error and that error is not equal to nil, then we do want to return that error. Outside of our delete keys closure, we want to specify a collection size. So I'll create a variable called collect size and I'll set it at 100,000. This is the optimal amount of keys that we can delete in one batch delete with BadgerDB. And so what will happen is if we have more than 100,000 keys with the set prefix that we're looking for, it'll go through, delete the first 100,000, and then it will go through and collect the next number of keys, however many there are. Let's reopen up the database, this time with a read-only transaction. And of course we have to pass in the closure so that we can access the Badger transaction. We then need to set up the iterator options for this Badger iterator which we're about to create, and the main option that we want to change is this prefetch values field. And what this essentially does is it makes it so that we can read the keys, but it doesn't have to fetch the values for the keys because we don't really care about the data. So we just find the keys and then we just remove both the key and the value without having to actually read the value itself. We can then create a new iterator with these options by passing the options into this function here. And then we want to defer closing the iterator so that it will properly clean itself up when it's finished. To collect the keys that we're going to delete, let's create a two-dimensional slice of bytes where the first dimension is 0 and then the second dimension is 100,000 length. Then we'll create a counter so that we can count how many keys we've collected in this particular piece of data. Now let's actually use our iterator to iterate through all of the keys that contain our prefix. So we create a for loop. We call it seek on the prefix because we're seeking out only keys with that prefix. We want to make sure that we're calling on the prefix, so we use this valid for prefix function as well. And then to continue going through our collection, we call it next to go to the next key. We can then copy the key itself by calling it item key copy and passing in nil. And this will just take the key and then put it into our keys for delete piece of data using the append function. Then we can increment our counter. We can then run an if statement which will check to see if the keys collected counter is equal to our collection size variable, which is our 100,000. And if that comes back as true, we'll run the delete keys closure which we defined above on the two-dimensional byte slice that we defined with all of our keys inside of it, and this will then delete all of the keys. And again, we're using that syntax where we're checking to see if there's an error and the error is not equal to nil. And if it is not equal to nil, we'll just call a log panic on the error. Now after we've deleted the first 100,000 keys, we just need to recreate an empty two-dimensional slice of bytes for the keys delete data type, and then we need to reset the counter. Then down here we have another if statement which checks to see if our counter is above 0 but below 100,000. And if it is above 0, then that means that we do have keys to delete, so we can then delete them down here with this little statement. And then finally we can return nil and close out of this function. Before we go further with writing the logic for our UTXO set, we need to modify our blockchain methods a little bit because some of these methods are going to be ripped out of the blockchain file and then put into the UTXO file. And we also want to change this particular method, which is going to stay on our blockchain, so that it corresponds with that output structure that we created rather than passing back just an array of transactions. So instead of taking in the public key hash, we'll make it so that it takes in nothing, and then the return type will be a map where the key is a string type, and then the value is a TX output structure. Basically, we want this function to go through all of our transactions and find all of the unspent outputs in those transactions. So first we need to create the two maps. Then, as we were doing before, we'll create our iterator, and then we want to iterate through each of the blocks, and then more specifically iterate through each of the outputs. Now down here we're calling the if is locked with key function on each of the outputs and passing in the public key hash, and you can see we're getting back an error because we're not passing in this public key hash anymore. So instead what we want to do is take our outputs and put them into our UTXO map with the string being the output's ID. So we'll take our entire map and put it into this outs variable, and then we want to go and put each of the outs that we're iterating through into the outs outputs field, and then we want to put that back into the map itself. Now down here we're iterating through each of our inputs, and we're checking if those inputs uses the key with the public hash. All we want to do is delete that if statement and then just leave the rest of it alone. Now at the end of the function we just return the UTXO map, and now everything is correct. Now we can go back into our UTXO.go file and set up the Reindex method for the UTXO set. First we want to alias the database, so we'll create a little variable called db and we'll bind it to blockchain database. And then we want to go through and call delete by prefix with our UTXO prefix inside of it, so that we can clear anything that's inside of our database which has this particular prefix attached to it. We can then call the find UTXO method on the blockchain inside of our UTXO set so that we can get all of the UTXOs which are inside of our blockchain. And then we can run a badger update so that we can actually read all of these into our database. So we'll iterate through all of the UTXOs, get out the indexes and then the outputs themselves. We want to decode the index into bytes. And then we want to take our UTXO prefix and affix it to the front of our index. And then we want to push it into the database using our transaction set function. So now this Reindex method will go through, clear out our database with all of the prefixes attached to it, and then rebuild the set inside of the database. Let's also create an update function which will take in a block and then use that block to update the UTXO set inside of our persistence layer. Again, we'll just alias the database. Then we want to run a read-write transaction on our Badger database again. Inside of this read-write function, we want to iterate through all the transactions. Then we'll run an if statement to check to see if the transactions are Coinbase or not. And if they aren't Coinbase transactions, then we want to iterate through all of the inputs in our transactions. For each of the inputs, we'll first create a transactions outputs structure, and then we'll take the inputs ID and affix the UTXO prefix to the front of it, and then we'll go into our database and get the value attached to that input ID in the database. And this will give us an item, and then we can just get the value from the item. We then want to take that value and deserialize it into an output structure, and then we want to iterate through each of the outputs inside of that output structure and check to see whether or not the outputs index is not equal to the inputs output index. So remember, our inputs contain a reference to the output that created the input, and they also contain an index for the output inside of the old transaction, and an unspent output obviously is not attached to an input, whereas a spent output is attached to an input. So we can verify that an output hasn't been spent by knowing that it hasn't been attached to an input. So we'll take any of the outputs that are not attached to the input that we're iterating through and put them into this updated outs outputs field. using the append function. Afterwards, we want to check to see how many outputs are in the updated output structure. If this is equal to 0, then we'll go through the database and make sure to delete any of the input IDs that are in the database, if there are any. Otherwise, we want to take all of the outputs inside of here and push them into our database with the MID as the key, and then the output itself serialized as the value. Now we need to create some logic to account for any of the Coinbase transactions that are inside of the block. So we'll create a new output structure, then we'll iterate through all the outputs inside of the Coinbase transaction and automatically push them into our database. So here we're iterating through the outputs and then appending them to our structure here. Then we're adding the prefix to the transaction ID and then setting them in our database. And the main reason why we always want to add a Coinbase transaction to our database is because the Coinbase transaction is always going to be unspent if it's on the latest block. So if a miner started to mine block B when these transactions were being made, then a Coinbase input and an unspent output would be created on block B, and the transactions would look something like this. And so we would have 3 unspent outputs on this block. Now there's one more quick helper method that we want to create for our UTXO set before we start to take the blockchain methods and pull them into this file. And this is just a method that will allow us to count how many unspent transaction outputs are inside of our set. So first we just alias the database, and then we create our counter. Then we want to open our database with a read-only transaction. We then want to create an iterator through Badger, and then we want to iterate through only the UTXO prefix keys inside of Badger, and for each of the keys we want to increment our counter. Then afterwards we can of course return the counter, and this will make it easy for us to count the UTXO set. Now the first method that we want to move from our blockchain.go to our UTXO.go file is this method here called find unspent transactions. So for now I'm just going to cut it out of the blockchain.go file and then paste it into the UTXO.go file. And then I want to change it to be a method on the UTXO set rather than the blockchain. The function signature itself will stay the same, so we're still going to pass in the pub key hash and then pass out an array of transaction outputs, but we do want to eliminate this call to chain find UTXO, and instead we want to alias the database so that we can iterate through our persistence layer because we've already found all of the transaction outputs, and then we can apply the logic that's in this function to the persistence layer. So instead of creating a for loop which goes through the unspent transactions, we create a view read-only transaction inside of our Badger database, and then we create an iterator so that we can iterate through our prefixes. As we're iterating through each of our prefixes, we want to get the items out of our database, and then get the values from the items, and then deserialize those items into a set of outputs. And then like we were doing inside of this part of our old function, we just want to iterate through each of the outputs inside of this new outputs variable that we just created. Call out is locked with key with the public key hash, and then append it to this UTXO's variable. So we can just cut that little for loop out from inside of this for loop and just paste it in here, and then we can just delete this part. The one minor thing that we do want to change about the for loop is make it so that it iterates through outs.outputs rather than tx.outputs, because that's what our variable name is here. And now this function will go through our persistence layer and find the balance for a user based on their public key hash. So it goes through, finds all of the outputs that are attached to that user, and then it passes them back, and then we can use them to find how many tokens are assigned to that user. Now the other method that we want to move from the blockchain.go file to the UTXO.go file is this find spendable outputs method, which is the one that allows us to create send transactions inside of our blockchain. Again, I'm just going to cut it out of this file and then paste it into our UTXO.go file. Again, we want to change the method to a UTXO set rather than the blockchain. And we can remove this call to chain find UTXO like we did in the function below. And instead we want to alias the database. Now again, it's just a matter of reading through our database and then iterating through each of our prefix keys like we were doing before, and then just applying the logic that we have here to the values inside of the database. So first we just need to get the item out of the database, and we want to specifically get the key out and the value out. Then we want to trim the prefix off of the key, and we can do this with this bytes trim prefix function. Then we can take the key and encode it into a string, and then take the value and deserialize it back into an output structure. In the old function, we iterated through this unspent transactions value, and then iterated through all of the outputs of these transactions. Now all we need to do is iterate through all of the outputs of our transaction. So we can remove all of this stuff, and then just take all of the stuff that was inside of that for loop and just paste it here. So we're iterating through each of the outputs, grabbing the index of the output and then the output itself, and then we're just checking to see if the output has been locked with our public key hash, and if the accumulated amount is less than the amount that we're looking for. And if it is, then we'll take the accumulated and add it to the output's value, and then we can take and add this output's index to the unspent outputs map that we're creating. And now the function should work as it did before, except this time now it's reading through our persistence layer. Alrighty, so now we've created all the methods that we need for our persistence layer. Now we do need to fix some of the errors that we have inside of our transaction.go file. Mainly the error that we have with this function here called new transaction. So as it is now, we're pushing in a reference to the blockchain, but instead we just want to push in a reference to our UTXO set. And once we've done that, we can come down here where we're calling the find spendable outputs function and change this from the chain to the UTXO set. Then down at the bottom of the function, we had a chain.signTransaction call, and we can just change this to UTXO.blockchain.signTransaction instead. Now let's head over to the command line interface and add a reindex command to the command line interface, as well as fix the other commands that we have inside of here. In our print usage, we want to add the reindex UTXO command. So this will rebuild the UTXO set when we call it. Now we can come down here and create a function which will allow us to actually do that. We'll just call this Reindex UTXO. We'll create the blockchain using our continue blockchain function, and then we'll defer closing the database, and then we need to create the UTXO set and pass the chain inside of it, and then we can call UTXO set.reindex. And then finally we want to count the transactions inside of our UTX set, so we'll use the count transactions function that we just created, and then we can print out how many transactions are in our set with this line here. Also, because of the stuff that we've refactored from the chain to our UTXO set, we have some errors for this getBalance function and for the send function. For the getBalance function, we want to add our UTXO set. So we take the blockchain that we're creating, pass it into the UTXO set, and then down here, instead of calling chain find unspent transactions, we can now call UTXO set find unspent transactions. And then the rest of it is as it was from before. Our send function is the same thing. We just want to add our UTXO set to this function. So again, we take the blockchain that we're creating here, and then we pass it into our UTXO set. And then with the new transaction method, we just want to pass in the UTXO set instead of the blockchain. Now notice that this add block function is throwing an error, and that's because the add block function doesn't actually return the block from it, though we actually do need it to so that we can call UTXO set.update on that block. And this is just a matter of going into our blockchain.go file, going to the add block method, and then adding a return type of a pointer to the block, then taking the new block that we're creating here and just returning it from the function. And you can see that this corrects the error inside of our send command. Now let's create the reindex UTXO command flag, add a case for it to our switch statement, and then throw in an if statement for it so that it will properly work when it's parsed. And now we can go ahead and run this application with our command line. Let's first go ahead and create a few wallets so that we can send some tokens back and forth. Then we can create our blockchain for one of these addresses. Now notice if I call get balance on this address, we actually get back a balance of 0 rather than 100, even though it mined the Genesis block and the Coinbase transaction in our blockchain. And this is because I deliberately left out a call to the reindex command when we create our blockchain. So as it is right now, we need to manually reindex the unspent. So as it is right now, we need to manually call the reindex command to set up the unspent transaction output set when we create a new blockchain. So we can run that command here, and now you can see it says done. There are 1 transactions inside of the UTXO set. And now if I go and run the get balance command on that address, you can see now it shows us that we do have 100 tokens attached to this address. Let's come in here and make it so that it's automated when we create the new blockchain. So all we have to do is just add the UTXO set by taking the blockchain that we create here with the init blockchain command and just pass it into the UTXO set. And then we can just call reindex after we create our blockchain. I can run all of the other commands that we have in our blockchain. And you can see here we now have 2 unspent outputs in our blockchain because I've run 2 send commands between our 2 wallets. Alright guys, well I hope you enjoyed this tutorial. If you did, feel free to subscribe and like. If you have any questions or comments, feel free to leave them in the box below. And if you disliked it, then by all means downvote it as much as you like. Have a good night.